Excellent.
May
Very
recording.
good. Ian now is going to present a statistical inference associated to verification. Thank you, Thank you, Ian.
Right, okay. Well, so far in the last couple of talks, you've had a lot of information on a lot of different forecast verification measures. This is a much wider idea. We're not looking at any particular measures, although we are, because we've got some simple examples. We're discussing really the need for taking into account uncertainty when you calculate a forecasting a verification measure, and doing it via statistical inference. Now you can do various hypothesis testing things, or you can find confidence intervals. And confidence intervals or other similar intervals are generally more useful. So most of this talk is going to be on them, with a bit of hypothesis testing at the end. I believe that the background of people on the course is very broad in terms of how much statistical inference they've done. So I hope that most of it will be intelligible for those who haven't done much. But at the same time, I hope there's one or two little nuggets in there which will expand the knowledge of some of the more knowledgeable. So let's see how we get this thing working. No, that's okay. Yeah. So I'm going to explain the basic ideas of statistical inference. Some are quite old, some are newer, and mention a few misunderstandings. And we've got a simple example to illustrate the some of the things I'm talking about. So the framework for statistical inference is that you've got some data and you consider that they're a sample from some larger population. The classic thing, not in forecast verification, but in general, is you take a sample of people. You want to find out something about a population of people, you take a sample. For instance, in the UK at the moment, once a week, we get told how many people in the population have currently got antibodies to COVID-19. They obviously haven't found out from everyone. What they've done is take a sample and then use that to make a projection as to what it is in the population. The population, when you're looking at verification measures, is a bit more nebulous. It's a sort of theoretical population of all the possible similar forecasts and observations that you could have taken. You've got some data, you could have taken other. There's this theoretical population that you could have sampled from and got different answers. And what you're looking at is the variation that happens when you take different samples from the same population and trying to work out what the value of a verification measure is in the population. As one of the Barbaras said, I can't remember which, there's no such thing as truth, but for the purposes of this lecture, I'm going to assume there is, and that's what we're trying to get. We're trying to get information on that truth. So the things we're usually looking at, the things we're trying to estimate, are called parameters. For instance, the proportion of population with antibodies, or some sort of population correlation between forecast and observed temperatures. There's three main types of inference. Point estimation is where you just give a single number. Because even if you're only getting a single number, there are different ways of doing it. And you're looking at the sort of best way of doing this in some sense. But it doesn't give you any indication of the uncertainty associated with that number. And that's where interval estimation comes in. You quite often see a number quoted and then plus or minus, and it's plus or minus a standard error usually that has been put in there. But there's no reason in many cases why the uncertainty associated with an estimate should be symmetric. So just doing plus or minus is a bit crude. It's better to go a step further and construct a confidence interval that's got a specified level of confidence of including the underlying population value. Then you can do hypothesis testing. There are circumstances where that's very useful. If you've done 2 different forecasting procedures and you want to know which is better, you may look at the estimates you've got from the 2 procedures and say, and formulate the hypothesis that really the underlying performance is no different, and test that null hypothesis. For instance, if we'll be later on looking at correlation, is the correlation in for one forecast better than for the other, or could it just have arisen by chance? And we're going to emphasize interval estimation. These data came from CAIO years and years ago and have just sort of floated around in slides for a while. The only thing you need to know about these data is it's a time series of 44 years. It's the mean sea surface temperature in this Nino area, and you've just got one measure for each year. So it's a time series of 44 sea surface temperatures. That's really all you need to know. So it's a pretty primitive example, really just for illustration. This ties in nicely with the example that Marion gave. We could compare the forecasts that we've made. I forgot to say, we actually had 9 forecasts of sea surface temperature. I'm just going to be looking at 2 of them, the ones that seem to do best and worst. We could, and I hope I can go backwards as I can. So let's go forwards a bit and then go backwards. There's a couple of scatter plots there. You can see the one on the left, these are not nearly as close to a straight line as those are. For forecast 1, we have a correlation coefficient of 0.767. For forecast 2, 0.891, and you can actually see from the scatter plots the reflection of those numbers. So you can look at the actual numbers, the actual surface temperatures, and get a correlation coefficient. So that comes from the continuous side of things. But as Marilyn showed, you can, by putting a threshold in, you could convert that into a binary data. And what I've done here is just look at which years the sea surface temperature was above the mean, which years it was below the mean, and similarly for the forecast. And I'm going to use probability of detection, which is also known as hit rate, as the verification measure, which is very similar to what Marion was doing. The value of these measures would be different if we had a different set of forecasts and observations, although we've actually taken all we know about those 44 years, so the population is pretty artificial, but we really want to know what's going on under the surface. So we've seen a scatter plot of the two sets of data and what the correlations were. We can also tabulate them. Here's our 2x2 contingency table. So where's my cursor gone? The observed, this is the observations now. So there were 13 occasions when we observed the temperature being above the threshold and 8 when it was below. So sorry, try that again. There are actually 13 plus 8, 21 occasions when the observation was above the mean. Of those, we forecast it correctly on 13 occasions, and we got it wrong on 8 occasions. Forecast 2 did a lot better. It got it right on 19 occasions and wrong on 2 occasions. We're looking at the probability of detection, POD, and that is, in this case, it's 13 over 21. In this case, it's 19 over 21, which in numerically is those numbers. So approaches to inference, there's what you might call the classical frequentist parametric inference, which is probably the dominant inference method for the first half and into the second half of the 20th century. Bayesian inference, well, given that it's associated with Thomas Bayes, it's very old indeed, late 1700s, but it became increasingly popular from probably about the 1950s, 60s onwards, and has a very strong following that says that you should always use Bayesian inference. But any form of inference has got pros and cons. So this has got cons as well as pros, and so it hasn't taken over the world. People still use classical parametric inference. Parametric inference usually assumes something about the probability distribution of the data that you've got, whereas non-parametric inference doesn't. And it's typically much more data intensive. You need much bigger computer power to do non-parametric inference. And then there's decision theory where you incorporate loss functions and so on. Two things noted at the bottom. One is the likelihood function, which is the joint probability distribution of the data viewed as a function of any unknown parameters that you're interested in. That is central to both approaches 1 and 2. The likelihood function is the key function for telling you about what's going on. It's a probability distribution of the data, but because you're interested in parameters, you view it as a function of the unknown parameters. And the other thing here is that we're getting into more and more computer intensive techniques coming from things like machine learning and artificial intelligence and things. So I'm going to look at each of these things: a confidence interval, Bayes interval or credible interval, and one type of non-parametric interval, which you get via the bootstrap. I put that in brackets. I don't think I will actually say anything about prediction intervals. There's 2 or 3 slides there. You can always ask about them later or in a drop-in session if you're particularly excited by them. I'm not that excited by them. So a confidence interval. The key thing about a confidence interval is that the interval is considered, well, is a random variable, whereas the parameter you're trying to estimate is fixed. So we've got in this little diagram here, where it says 0, this is an example where the true value of the parameter was 0, and you take lots and lots of samples of data. For each sample of data, you calculate an interval. And these are, I think there's about 50 intervals there. And what will happen is you have constructed a specified level of confidence. Most common one is 95%, sometimes 99% or 90%. But if you've got a 95% confidence interval, it means that if you spend a lot of your life doing confidence intervals, then 5% of the time you're going to miss. Your interval won't include the true value, the population value of the parameter, but 95% of the time it will. But the crucial thing about a confidence interval may sound a bit sort of picky, but it's very crucial. It's that the interval is random, the population value is fixed. The confidence level is the long-run probability that the intervals include the parameter. It's not the probability that the parameter is in the interval. The probability is associated with the interval, not with the parameter. We'll see shortly that for Bayes intervals, it's the other way around. So, next thing I'm going to do is to look at some confidence intervals for the probability of detection in the example that we've got for the two forecasts that we've got. I'm going to call the proportion of occurrences of above, keep losing my cursor, there it is. I'm going to call the proportion of current occurrences of above average sea surface temperature. Sorry, I'm going to call POD. It's the proportion of occurrences above average sea surface temperature that were forecast. I can't read my own slide now. I'm going to call that P, so that's the sample pod. I'd like to know what would happen if this was just a sample from a bigger population. What's going on in the population? What's the confidence interval for the probability of detection in the population? And I'll call that theta. And what I've got here is a standard one of finding a confidence interval for probability of success in a binomial distribution. If you've done any stats at all, you've probably come across the binomial distribution. And if you've done any inference associated with it, you'll have various Gaussian normal approximations which give you probability, give you confidence intervals. So there's a couple here which I'll skim very quickly. You can approximate the distribution of P by a Gaussian distribution with mean theta and variance P1 minus P over N. And if you do, you get an interval which has 95% chance of including theta will be of that form there. Slightly better approximation, still assuming a Gaussian distribution, is you, instead of having a variance given by the sample quantity, you have variance given by the parameter. That leads you to a quadratic equation whose endpoints are the endpoints of your confidence interval. There's also something called an exact interval. It is exact, it's based on the discrete distribution of the binomial distribution, but the problem is because the binomial is discrete, it's only exact for certain probabilities. There are jumps between it. So for instance, you couldn't get a 95% interval necessarily. You might be able to get a 97% or a 94.5, but you can't get exactly what you want. This little yellow table is going to be repeated several times with things added to it. In this one, I've just got I only want to look at the first three things here: the crude approximation, crude confidence interval, the better approximation, and the quotes exact one. The forecast one, there's very little difference between the crude and the better approximation. That's because P is quite a long way away from 0 or 1. So the normal approximation, Gaussian approximation, is pretty good. So doing the more sophisticated one doesn't make a lot of difference. The forecast 2, things get a lot worse, especially if it gives you a range that goes outside the values 0 to 1, which is, well, not possible. And that's because for forecast 2, where P is actually quite close to 1, the Gaussian distribution is not very good. Gaussian approximation is not very good. The exact interval is wider than the others, but that's probably because it's not really a 95% interval. The others are supposed to be 95% intervals. The exact one is probably got an interval confidence coefficient greater than 95%. So moving on to Bayes intervals, also called credible intervals. What you need in the Bayesian approach is some prior information. Before you actually collect your data, you say you're not entirely ignorant about what you think theta is going to be. You've got some prior experience of data like it. So when we're looking at probability detection, you know that for these sort of data, you're expecting probability detection to be somewhere in the middle range, perhaps 0.4 through to 0.7, that sort of numbers. You're not expecting it to be 0.1, you're not expecting it to be 0.95. So you've got some prior information. Why not incorporate that? So what you do is you quantify your prior information into a prior distribution. You combine it with the likelihood function, which is what the data is telling you about theta, and give a posterior distribution for theta. So Bayes intervals are a different sort of animal from confidence intervals. They assume that theta is random and not fixed. And so they get a posterior probability distribution, and then you can chop off 2.5% at each end of that distribution. So you've got 95% in the middle, and that gives you a 95% Bayes interval. You've got to choose a prior distribution. That's one disadvantage. So how you do that is not always straightforward. I've given on this slide some information about what I've done in the example, and using a so-called beta distribution is usually a good idea for binomial, but you don't need to worry about those details. Okay, so here's an example for forecast one. These two things over here on the left are two different prior distributions. The solid line says, I don't know anything. P could, actually it should be theta along the bottom there. Theta could be anything between 0 and 1, and I don't have any reason to prefer one value to another. That's pretty unrealistic. You have some knowledge. So I've got another prior distribution here where I think that it's probably likely to be centered somewhere around about 2/3, but it could be anywhere between about 0.4 and 0.85, 0.9. So that's my posterior distribution, which is from this family of distributions here. And over here, I've got the posterior distributions. This is combined, these two things over here, with the likelihood. And you can see, how do you get your interval? Well, what you do is you chop off, if you're doing a 95% interval, chop off 2.5% in that tail, 2.5% in that tail, and wherever that lands, that's your interval. I should have had this on the same page as the pictures. The informative prior actually has a mean 2/3. It's narrower than the informative prior is narrower than, sorry, the informative posterior is narrower than the uninformative one, as you'd expect, because you put more information into it. So you should be able to sort of compress your views a bit. It's also shifted a bit to the right, sorry, to the left. No, to the right. I'm getting a bit confused now. It's shifted downwards to forecast 2. Yeah, what's on that slide is not referring to the picture. It's referring to the table down here. For forecast 2, the interval has been shifted down a bit, and that's because your original estimate from your data was up in the 0.9s. Your informative prior had mean 2/3, and you're compromising between those. So you've shifted it down a bit from the other ones. Okay, third type of interval, bootstrap interval. My data set for forecast 1 consists of 13 successes and 8 failures. What I'm going to do is to take B samples, where B is going to be a big number, of size 21, from these 21 values, and calculate P from each sample. When you talk about taking samples from a population, almost always you sample without replacement. You sample one person or object, and then you sample another one and another one and another one. You keep going with different ones. So the key thing here is in the bootstrap, you're sampling with replacement. Now, I've got a visual aid here, if you can see a little picture of me somewhere. There's a bowl, and in here, I've got 13 dark coloured pebbles, and I've got 8 pale pebbles. And what I do is I shuffle around, I pick one out, that's a dark one, I record it, but I put it back. Take another one, another dark one. I record it and I put it back. And I do that 21 times. And from there, I work out what P is for that sample. And then I do that whole thing 1,000 times. And that gives me a distribution of values of P. I've got B values of P. And for a confidence interval, well, I said for a confidence interval, this is a bootstrap interval. For a bootstrap, for confidence level 1 minus 2 alpha, I find the B alpha smallest and the B alpha largest. So if B was 1,000, then I would look for the 25th smallest and the 25th largest. And those two things would define the endpoints of my bootstrap interval. And that's on that slide. There's my bootstrap interval, and you can see that it's actually very close to what we had before in using other methods. So in this particular example, the various methods don't diverge too much. In other examples, they will diverge rather more. What I've just done, this technique that I've described here, picking these things out and putting them back again, and looking at the ranked data, is called the percentile method. And it's pretty good, but it does have some drawbacks, and you can improve on it. And there are various variations on that theme, things called basic bootstrap and bootstrap T intervals and so on, which I'm not going to go into at all, but you can look at at your leisure later. And they all share the idea of sampling with replacement. That's the crucial thing. It's called bootstrap because you're essentially pulling yourself up by your own bootstraps. One modification which I will mention here, and I'm actually going to come back and mention another couple of modifications later. But one thing to mention is that often your data are not independent. They either have temporal or spatial correlation. And in that case, you need to adapt what you're doing. If you've got temporally correlated data, you can use a so-called block bootstrap. You don't take your observations one at a time, you divide them into blocks so that the blocks are big enough that they're pretty much independent of each other. And then you take samples of the blocks with replacement. Oh yeah, when I looked at this one earlier, I said it was the percentile bootstrap interval is not very different from any of the others, but the one thing it has going for it is it doesn't make any assumptions at all. The first couple use Gaussian assumptions. The Bayes ones use prior information, which you've got to get from somewhere. Okay, I'll now move on to look for confidence intervals for differences. Suppose we've got two forecasts or forecasting systems. We want to compare their probabilities of detection by finding a confidence interval for the difference between the two underlying parameters, θ1 minus θ2. It's pretty clear that in the present example, we've got small samples, the interval is going to be very wide. But as an illustration, we'll look at a 95% confidence interval for the difference in pod for our two forecasts that we had earlier. And again, you can use a Gaussian approximation to find an interval, and it comes out, a 95% interval comes out as this. It's between minus 0.53 and minus 0.05. Not surprising, given that you've only got such a small number of observations. It's very wide, but it doesn't include zero. And that implies with 95% confidence that θ1 and θ2 are likely to be different. Now let's look at percentile bootstrap interval for percentile bootstrap intervals for differences. What I do then is I take a sample from my bowl again with 13 ones, or 13 dark ones and 8 pale ones. There are pale ones in there, by the way. I'm not sure I showed you one. And calculate P1 for each sample. I then have another bowl. This bowl's also got 21 pebbles in it, but of those, 19 are dark ones and 2 are pale ones. And I do the same sort of thing again and calculate P2 for that sample. So I calculate that and do it B times. Typically B equals about 1,000. And I'll rank the values of P1 minus P2. And again, I'm looking at percentiles of distribution. So if I wanted a 95% interval, I'd look at the 25th smallest and the 25th largest. And those are the endpoints of my interval. And the interval there is minus 0.52 and minus 0.05, very, very similar there. Only difference is a 5.2 instead of a 5.3. So again, that's suggesting that the two values of pod for the two different forecasts are different. Oh, I didn't want you to see that red bit. Think about this compared to what we found before. If you go back to the intervals for P1, but based on P1 and P2 alone, in other words, intervals for θ1, intervals for θ2, then in every case they overlapped can I get back to one pretty quickly? If you look at that, the upper end of that interval is higher than the lower end of that interval. So that's saying that plausible values for P1 overlap, θ1, overlap with plausible values for θ2. That's the opposite of what we've just found. So which one of these is right and which one of these is wrong? Now, if you were all not muted, I would expect you all to be saying simultaneously, well, this is the right one. The overlapping intervals is wrong, because that's what, that is the correct answer. The flaw with looking at overlapping intervals is that it's including a combination of two extreme events if you've only got a very small overlap. If you've only got a very small overlap, then this interval you have managed to occur right at the top of the end of it, whereas the other interval, forecast 2, you've managed to occur at the very bottom end of it. So you're basically combining two unlikely events. So the probability of that happening is not 5%, it's less than that. So don't base your conclusions on overlapping intervals. Always go for the difference. Go to the difference. I'm not finished with intervals for differences because the intervals above assumed independence of P1 and P2. And if they're positively correlated, the interval will be narrower. Now, it seems likely, correlated is perhaps not the right word because you're not calculating a correlation because you're looking at binary things here, but positively associated, because you would expect that on the occasions that forecast 1 got it right, it was more likely than not that forecast 2 got it right as well. They wouldn't be completely independent of each other. There'd be stuff going on in the atmosphere that suggested strongly that the temperature was going to be above the mean, and both forecasts would say that. It's only in the middle of the distribution where they're going to give different answers. So we haven't taken independence, we haven't taken non-independence into account when we calculate our intervals so far. So to take account of the pairing between the forecasts, we do a bootstrap in a different way. I'm now sampling from a population of size 44. That was all my years. And for each year, I've got a triple I've got a forecast. So I've got forecast 1, I've got forecast 2, and I've got the observed. So I've got that triple for each year. And what I now do is I sample with replacement from that size 44 population. And for each time I do that, I calculate, well, I do that. Each time I do that, I calculate P1 minus P2, and I repeat that B times. And I rank the B values of P1 and P2, and again, take the percentiles as the endpoints of the interval. And in that case, the 95 percentile interval is minus 0.48 to minus 0.1, which you probably don't remember, but oh, it's on there, isn't it? No, it's not on there. There we are. There's the previous one, 52 and 5. It's gone to 48 and 10, was it? The main thing is that it's narrower, and that's what we'd expect if there was some positive association between the two forecasts. So again, another aspect of taking differences is don't assume independence unless you're really sure of it. And it's very unlikely to hold, because generally one forecast will do well when another forecast does well. They won't be completely randomly independent of each other. Okay, so a little bit, a few minutes left. A little bit on confidence intervals for the correlation coefficient. Here, I'll call my sample value R, and I'll call my population value rho. And again, we've got some approximations based on the Gaussian. The first one is just approximation of the distribution of R, and this is the distribution of this quantity. It gives you a better approximation. And you can also get Bayesian and bootstrap approaches. I'm not going through all the details. Oh, that came in last, did it? I'm just going to give you some results from this. There are intervals for the normal approximation. Those are confidence intervals. That's a better approximation. I haven't given a Bayesian one on here. And then the percentile bootstrap one is at the bottom there. And again, the advantage of bootstrap is it doesn't make distributional assumptions. Therefore, if you're a bit dubious about any distributional assumptions you've made, you should use something non-parametric, such as the bootstrap. I'm going to skip prediction interval because I'm getting close to my time, and go on to hypothesis testing. Quite often, the interest in uncertainty is to do with, could something have been, something that I've observed, been due to chance, and therefore might not have happened if I'd taken a different sample, or is it sufficiently different from what chance would predict that I've observed a real positive value of some verification measure? So there are two main types of hypothesis that you might be interested in. The first is the observed value that you've got compatible with what you might have observed if the forecast had no skill? And secondly, given two values of a measure for different forecasting systems, or possibly the same system at different times, could the difference in values have arisen by chance if there was no difference in the underlying skill? And those questions can be answered with a formal test of the null hypothesis of no skill in the first case or equal skill in the second case. And a test of hypothesis is often equivalent to a confidence interval. And hypothesis testing can be treated as a clear-cut decision process, if you like, but without any loss or cost functions. What you do is choose a significance level, often 5% or 1%, but it needn't be. You construct a critical region, that's a subset of possible data, for which H0 will be rejected. Critical region is basically data which you think is pretty unlikely if H0 was true. And if the data that you observe actually fall into that set, you'll reject H0 at whatever significance level you've chosen. So in our example, one of the forecasts had an R value of 0.767. Null hypothesis of rho equals 0. It's going to be pretty clear that's going to be rejected. A sample correlation of nearly 0.8 is going to be significant. The critical region here is going to be anything that is bigger than 0.295 or smaller than minus 0.295. That obviously is 7.767 obviously is. So we would reject the null hypothesis at the 5% level or indeed at much more stringent levels. There's one oddity here, is that I work with data from lots of disciplines. Nearly everyone would say we reject H0 at the 5% level. There's a substantial number of atmospheric scientists who say we reject this at the 95% level. Correspondence between confidence intervals and tests of hypothesis. If you've got a 95% interval, you will reject H0 at the 5% level if and only if the interval fails to include 0. There's this duality between hypothesis testing and confidence intervals. And so if the intervals are at 99%, the test will be at 1% and so on. This is just an odds and ends slide, if you like. It mentions decision theory, which we've seen the phrase, but that's it. For that, you need loss functions. You also need prior probabilities. Another thing that appears often is p-values. Not so much in atmospheric science, I don't think, but p-values are ubiquitous. It's the probability that the data or something less compatible with H0 than the data could have arisen by chance if H0 was true. And it's not the probability that H0 is true. This is so often misinterpreted. You can find the probability that H0 is true by a Bayesian approach, but not a p-value. A p-value is the probability of the data or something less compatible with H0 having come about if H0 was true. It's not the probability that H0 is true. There's been a massive amount of discussion of p-values recently. In 2015, a psychology journal banned them, said thou shalt not, if you put a p-value in your submitted paper, we're going to reject the paper. This was followed by much discussion, including American Statistical Association issuing a statement on p-values. And it published a special issue of the American Statistician containing 43 articles. So if you really want to get bogged down in p-values, there's the place for you. So what have we learned? When calculating a verification measure, there's almost always uncertainty associated with the value of that measure. And statistical inference can help trying to quantify that as uncertainty. Sometimes we wish to test a specific hypothesis, such as, are the new forecasts, is a new forecasting system better than an old one, or could the forecast better than other forecasts we've got, better than might have achieved by chance? More often, I believe that a confidence interval or some other type of interval is a more informative way of quantifying uncertainty. We've seen several types of interval, and there are also different ways of computing them. And the choice between intervals and method of calculation depends on the assumptions that you're making. Whether you're making assumptions about distributions, whether you're making assumptions about independence. Identify what assumptions you are making and then choose what technique you want to quantify the uncertainty in your verification measure. And try to understand your choice. As it says, in an ideal world, ask a statistician. And also, the final thing we learned was links between interval estimation and hypothesis testing, even though I skipped over that very quickly. We've only covered a tiny part of statistical inference. There's nothing on traditional non-parametric inference. Another, it's a bit like me saying you can get really bogged down in p-values. There are all sorts of subtleties associated with any of these intervals, like making sure you've got dependence accounted for in bootstraps. Knowing what you mean by an uninformative prior distribution is another one. You could argue that being completely flat is not correct. There's quite a lot of software out there. Some of it doesn't include method or formulae for quantifying uncertainty. If your software doesn't, that's no excuse for ignoring it. Supplement your software and write a bit yourself. And then finally, some references. The last two are the p-value stuff. Bootstrap methods, there's some good textbooks on bootstrap methods in general, but I thought I'd give Eric a plug because his are related to forecast verification. There's also an awful lot of good stuff on Bayesian methods out there, but I put in something which was related to climatology, and then I couldn't resist an advert for that particular book. So thank you very much for listening. And what am I doing now? Am I not stopping sharing or?
You can stop sharing. Thank you, Ian. Which is at the top, hidden.
Yeah, there we are. Right, I'm back in the Zoom world.
Yeah, it was excellent, actually. As usual, I learn a lot from your talks.
I don't see a question up to now. May I wait for a couple of minutes?
Stunned you all into silence.
There is so much to take in. Huh?
Well, can I just, Ian, I'm wondering if you want to comment on the p-value thing a little bit, because they're still absolutely mandatory in climate science. If you want to publish in Nature, there's no way that Nature seems absolutely anal about, and there's nothing, I mean, inherently wrong with them, right? It's just part of the likelihood. It's just how they're used, isn't it?
I think it goes, before I answer that last bit, I think it goes further than that in some circumstances, in that in some disciplines, it's very difficult to publish something that has a non-significant p-value. It's not just the p-value that they want a significant p-value. Yeah. If you've got a non-significant p-value, don't bother, because no one's interested in that sort of result. Sorry, you were saying that?
Well, just it's sort of how they're used, isn't it? I mean, it's the inversion of the conditional and all these kind of things, that dichotomous interpretation. It's not necessarily the p-value per se, is it? It's just the way that they're used.
Yeah, I think the p-value is a useful bit of information. There are various problems associated with use of multiple p-values. I mean, both from the point of view of someone does a study and does loads of tests, and some of those are going to be significant. So those are the ones that get published. And also, if you do lots, then the overall probability of getting at least one significant one is, well, it becomes almost certain.
We have a question, actually.
I think I object more to just sticking to, you've got to be significant at the 5% or the 10%. Actually quoting the p-value is a more useful way of doing things.
Can I make a comment? I think that the real key is that confidence intervals are so much more useful than p-values, and you can show, you know, insignificant confidence intervals as well as ones that are significant. But just giving that information that really represents the variability in whatever it is you're looking at it makes a huge difference. And then compared to looking at p-values, you know, and I think that is part of the underlying recommendation of some of these efforts to try to get rid of p-values, is that we need to really represent what's going on, not just show the p-value. And I agree with that issue of people cherry picking which ones they're going to show, and that is totally inappropriate. So it shouldn't be allowed in the literature. Anyway, that's just
also the fact that, you know, if you did the same experiment twice with the same test done, then the ones that have got the smallest p-values in one study are almost certainly not going to be the ones with the smallest p-values in the next study, because you know they're sort of reverting towards the mean, as it were.
Yeah, and just one last thing before I hand it over.
There's a question. I think like we should address this question first. I'm sorry for that. So question comes from Steven. The question is like, usually when testing scale of climate model using some metrics, for example, correlation of anomaly, it is required to test significance. How important is this? So basically, like how important to, like same, you know, discussion, but how important to have a significant correlation to measure the skill of a climate model?
I'm not sure how to answer that. I mean, just testing for significance is a bit just limiting, isn't it? Also, I mean, the question in the chat there is just saying, e.g. correlation of anomaly. Well, you probably want to look at several things anyway and just try and get a feel for interpreting what's going on rather than relying simply on one or two significance tests. I see we've got Laurie and Karen both with hands up.
Yes, okay, I'll go first. And my question is about the bootstrap. Do you have any guidance on how to decide how many repetitions to do for the experiment, the bootstrap? You did 1,000. Is there anything?
I think 1,000 is a sort of fairly typical thing. It depends on how complex your problem was. If it's a fairly simple one, you could probably get away with fewer. And if it's a pretty complicated one, then you may need more. Don't think there's a simple answer, but the great thing now is we've got computers that can do these things thousands and hundreds of thousands of times. So why not use it? I haven't personally got a computer like that, of course. This is just a laptop.
Thanks. So we have only 1 minute left. Karen, quickly.
I'll make it quick. This discussion of, you know, p-values versus confidence intervals, and which is better, which is worse, it's been going on for decades, as we all know. And I think I guess I'm kind of pushing back against what Barbara Brown said when she said confidence intervals are so much more useful than p-values. I think the answer is it depends. They both have value. Confidence intervals are good in the ways you said, but they're two numbers, an interval, two numbers. It's hard to show two numbers on a map, for example, at every grid point. But a p-value is a single number. You can show a map of p-values at every grid point. It's easy, it's easier. So they have their own pros and cons is one thing. And also when it comes to what Ian said, that if you do multiple times, you're going to have a probability 1 of a false alarm. the problem there is not with a p-value, but with alpha, right? The fixed significance level with which we're comparing the p-value. If you let go of alpha, 0.05, 0.01, the p-value itself carries information. We can look at it. It says something, right? Yeah, I don't know if I left any time for.
Karen, I'm
Yeah,
sorry for being a hard master, because the times are like I have to cover so many topics. So there's a good discussion I see in the chat. Maybe after the talk we can discuss. Okay, let me start.
I shall be at the first drop-in tomorrow if anyone wants to call me then.
And
Yeah,
Nachiketa,
yes.
just introduce yourself a little bit as well. We
Yeah.
all did that yesterday.
Okay, can you see my screen in a full screen mode?